Your feed is packed with battery miracle claims, phones that never run out, cars that recharge in seconds. Honestly, a lot of that is just hype. Even lithium-ion isn't a single technology. It's a whole family of chemistries, each with very different strengths in energy, power, and lifespan. But there's one idea that genuinely sounds like science fiction, yet is grounded in real physics. If you're new here, consider subscribing and hitting the bell icon so you don't miss future videos. Now imagine a battery made from diamond and powered by nuclear decay. Some companies claim it could last for decades, even thousands of years, and might start appearing in products as soon as 2026. So what exactly is it? What can it actually power? And what should you take with a grain of salt? Here's the concept. Take carbon-14, a radioactive version of carbon, and embed it inside a synthetic diamond. Over time, carbon-14 naturally decays into nitrogen-14 through a process called beta decay, releasing electrons. These electrons carry energy, and the diamond can convert that energy into a small electric current, similar to how solar panels turn sunlight into electricity. The diamond also acts as a built-in shield, trapping the radiation inside. But there's a catch. The power output is extremely small. Think microwatts, not the watts your smartphone needs. That's because carbon-14 decays very slowly, releasing only a few electrons at any given moment. So this isn't a never charge your phone solution. Instead, it's more like a slow, steady trickle of energy that can last for years. The long lifespan comes from carbon-14's half-life of about 5,730 years. After one half-life, the battery doesn't stop working. It just produces about half as much power. That's why you sometimes hear huge numbers like 28,000 years in marketing claims. Also, these aren't the kind of diamonds you'd wear as jewelry. They're lab-grown industrial materials, typically made using a process called chemical vapor deposition. Many designs use a thin layer of carbon-14 sandwiched between layers of regular diamond. This keeps costs down while maintaining strong radiation shielding. And since the radioactive material is locked inside the crystal structure, there's no liquid to leak or casing to break open. So why hasn't this been widely used before? Radioactive decay has actually powered machines for decades. In space missions, radioisotope generators, often using plutonium-238, convert heat from decay into electricity. That's how spacecraft like Voyager 1 and Voyager 2, launched in 1977, have continued operating far from the sun. But those systems are bulky, extremely hot, and expensive. They also rely on materials that aren't suitable for everyday consumer devices. The diamond battery idea came from a different angle: nuclear waste. In the early 2000s, researchers at the University of Bristol studied graphite blocks from old nuclear reactors. These blocks contain carbon-14, making them difficult and costly to dispose of safely. The breakthrough idea was to reuse that carbon-14, turning it into diamond and creating a battery where the structure and radiation shielding are the same material. For years, though, the concept stayed in the lab. The power output was low, and producing specialized diamond structures was too expensive. The real progress came with layered designs. Instead of making a solid chunk of carbon-14 diamond, engineers use a thin active layer surrounded by regular diamond. This approach delivers similar performance while using much less radioactive material. Once the battery becomes a stack of thin, repeatable layers, the focus shifts to scaling production, sealing the structure, and ensuring reliability, rather than crafting perfect diamond blocks. So why is 2026 being mentioned so often? It's not because of a sudden scientific breakthrough. It's about manufacturing. Modern chemical vapor deposition technology can now produce diamond films that are thinner and more uniform than ever before, sometimes just a few micrometers thick. It also allows precise control over how carbon-14 is distributed within the material. That precision is crucial. If the carbon-14 is too concentrated, the emitted particles lose energy before escaping. If it's too spread out, the battery becomes too weak. Getting that balance right is key to performance. On top of that, advances in electronics have improved how the battery collects and delivers charge. Better contacts and packaging reduce energy loss and help maintain performance over long periods. Early designs often struggled with efficiency because extracting power from such a tiny source without degrading the contacts was difficult. But now, that challenge is being addressed more effectively. In short, while nuclear diamond batteries aren't going to replace your phone battery anytime soon, they could become incredibly useful for low-power devices that need to run reliably for years, without ever needing a recharge. Early public prototypes of these batteries were often described as producing single-digit microwatts per gram. Newer designs are now commonly discussed in the mid-teens, with some labs claiming even higher performance. Even at around 15 to 20 microwatts per gram, that's still nowhere near enough to power a smartphone. But it's more than enough for ultra-low power sensors and devices that transmit data occasionally. Costs are also starting to shift. As the diamond layers become thinner and manufacturing processes get faster, the same amount of production time can yield more batteries. That doesn't mean they'll suddenly become cheap overnight, but it does explain why the conversation has moved from a cool concept to pilot programs and early customers. When it comes to key players, a few names keep coming up. Research connected to the University of Bristol helped bring attention to the idea of turning nuclear reactor graphite waste into carbon-14 for these batteries. In the United States, NDB Inc. has been actively promoting self-charging diamond batteries with extremely long lifespans, focusing first on industries where replacing batteries is expensive or difficult. In Asia, several teams and startups have shown prototypes and shared ambitious timelines, including one working under the name Beta Vault. Meanwhile, researchers in Russia have published work on similar beta-voltaic designs, though their path to commercialization is less clear. Established nuclear and materials companies also play a crucial role. They understand the complex world of regulations, handling isotopes, tracking materials, managing transport, and passing long-term safety tests. While a startup might build a working prototype, building a reliable supply chain that can pass audits is a much bigger challenge. One major bottleneck is carbon-14 itself. It's not readily available in large quantities. While some can be extracted from nuclear waste, the supply is limited and processing it is complicated. If these batteries scale up, more carbon-14 would likely need to be produced intentionally in reactors or specialized facilities. That process would require permits, long approval timelines, and public oversight, so growth would likely happen gradually, not instantly. On the diamond manufacturing side, things are more familiar. Industrial diamond producers already create durable diamond films for tools and electronics. For them, making batteries is more like adding a new product line using processes they already understand. Some are already exploring this shift because they have the equipment, materials, and quality control systems in place. So the race isn't just about physics, it's about manufacturing capacity, raw materials, and building trust. When it comes to applications, think long-term reliability rather than high power. These batteries are ideal for situations where you need a tiny, steady amount of energy over many years. Medical implants are one of the most promising uses. Devices like pacemakers typically last around 7 to 10 years before needing a battery replacement, which requires surgery. A longer-lasting power source could reduce both risk and cost. The same applies to drug delivery systems, biosensors, and nerve stimulators. Remote sensors are another perfect fit. Right now, a lot of money is spent just replacing batteries in hard-to-reach places like the Arctic, deep oceans, or inside industrial systems. A sensor that can run for decades without maintenance could completely change the economics. This would benefit areas like environmental monitoring, wildlife tracking, and leak detection. Space applications are also a natural match. Servicing equipment in space is extremely difficult, and every gram launched is expensive. A small but reliable power source that lasts for decades is very valuable for satellites and deep space probes. For everyday consumers, the reality will likely be less dramatic than the hype suggests. Instead of never-ending smartphones, we'll see always-on devices like smart locks, air quality sensors, emergency beacons, and RFID tags benefiting from this technology. The military is also interested, mainly for standby systems and embedded sensors. The limitation is clear. Lithium-ion batteries will still dominate when high power is needed. If a device requires significant energy output, traditional batteries or a direct power source will remain necessary. Safety and regulation are also important to understand. The word nuclear can sound alarming, but in this case it's more controlled than people might expect. Carbon-14 emits beta particles, which are essentially fast-moving electrons. These particles don't travel far and are relatively easy to block. They can't penetrate intact human skin, and the diamond layers provide an additional level of shielding. That's why carbon-14 is considered a low-energy radioactive material compared to those used in space power systems. Containment is also very different from what many imagine. The radioactive material isn't stored as a liquid or gas inside a container. It's bonded directly into the diamond crystal structure. There's no pressurized vessel, no moving fuel, and no simple way for it to leak. Even if the device were damaged, the material would still remain a solid diamond with the carbon-14 locked inside. That said, regulation remains a major hurdle. Even relatively safe radioactive materials must be carefully labeled, tracked, and transported under strict rules. Different countries also have different regulatory speeds and standards. Public perception is another challenge. If people hear nuclear battery without proper context, fear and misunderstanding could slow adoption, even if the actual science and safety are well understood. That's why companies put so much effort into clear testing and simple, easy-to-understand comparisons to help people feel confident about the technology. As for the timeline, if we do see real products by 2026, they'll likely appear first in industries that are already used to strict regulations and detailed testing, like aerospace, defense, and medical devices. Expect small production runs, high costs, and a strong focus on long-term reliability data before anything reaches the mainstream market. If these batteries do take off, their impact will be subtle rather than dramatic. You might see fewer battery replacements and less electronic waste. Sensors embedded in infrastructure, like bridges or pipelines, could quietly monitor conditions for decades without needing maintenance. Still, it's important to separate reality from hype. Radioactive decay is naturally slow, and there's no way to get smartphone-level power from it without making the battery extremely large. So yes, forever power is possible. But it's more like a gentle, constant trickle than a powerful surge. Diamond nuclear batteries won't replace lithium-ion batteries, and they won't eliminate the need to charge your phone. Their strength lies in delivering tiny amounts of power over incredibly long periods. That makes them perfect for specific use cases, like medical implants, deep-sea sensors, satellites, smart tags, or structural monitors that you install once and don't have to think about again. If 2026 does bring the first real products, the early successes will likely go unnoticed by most people. And that's okay. What really matters is how the technology performs over time in terms of cost, carbon-14 availability, regulation, and public trust. If you had the chance to use a forever battery in one device, where would you want it most?